Okay, here is the lecture on activation energy and the activated complex. And we're going to work through and talk about what activation energy means and what the activated complex looks like. And we'll do some mechanisms and talk about how this all fits together in terms of rates. So again, the focus here is activation energy and reaction mechanisms. Let's start off by looking at the Arrhenius equation. When we look at the Arrhenius equation, we have some constant, and that constant, K, right, or the rate constant, is equal to a factor, right, this frequency factor, A. And that's important. We'll define that a little bit further in the next slide. But the thing that we're going to focus most on is this activation energy. So this E in here, this one right here, right? The little e, sorry, I'm trying to point right there. The little e. Little e, right, it means exponential. That's a function on the calculator. It's it's not it's the ln. It's the opposite of ln. So um, if you know functions like log and 10 to the x, this is ln and e to the x, right? So you got to make sure you're using that appropriately. The other thing you have to make sure of is that when you apply this equation, that you use the negative sign in the equation. So it's negative E sub A over, so it's negative E sub A activation energy over RT, right? And that's all raised in terms of the exponential. It is the exponential term, okay? It's really important. And the temperature in this always has to be in terms of Kelvin, okay? Here we go. So what is activation energy? Well, activation energy is literally the amount of energy that is required to get over the hump and get to products, right? And so the idea is that you've got the reactants on this side in some sort of energy, right? And in order for them to get to products, again, there has to be this certain amount of energy applied or put into there. And again, that's that E sub A term, activation. Okay, so let's look at a reaction. And in this reaction, what is happening? Well, what's happening is if you look here, the basically the nitrogen and the carbon are switching places. Okay, and so in this model, we've got the nitrogen sandwiched in the middle there. In this model, we've got it on the end. And so let's take a look at this. There's a energy barrier to reactions, and activation energy is the energy needed to convert reactants into an activated complex. And so if you remember, it went something like this. It went up. The activated complex is sitting right up here. Okay, so that's what we call the transition state, and that then falls off and goes to products. So you got reactants over here and products over here. The activated complex is a species with some partially broken and partially formed bonds, and it's high energy because of those partial bonds. So again, back to that idea of the reaction where we're going from the N triple bond C to C triple bond N in the product. The activated complex is some form here where you've got the triple bond still intact, but the methyl group, and this is called a methyl group, the CH3, is actually migrating essentially from the nitrogen to the carbon. and that's the activated complex. That's that transition state, and then it um, falls off to. So somehow, right, this bond has to weaken, and this right CH3 is kind of migrating in this direction, or you can think of it as this N triple bond C is rotating in this direction, right? So that the carbon carbon bond will form as opposed to nitrogen carbon bond. So again, each movement here is an approach to the activation barrier. And so as this moves up the slope, this shift, right, begins to occur. And the more it moves in that direction, the more it gets towards this activation barrier. And once it gets up here, then essentially the all the energy needed for it to go has been put in, and it moves to the other side. Okay, so we can look at again data, and we can look at these rate constants at different temperatures, and can figure out a little bit about what's going on. This is the temperature dependency of rate constants. Okay, so in the Arrhenius equation, there's temperature, right? That temperature influences the rate constant K. Well, you also have activation energy influencing that. You also have this factor of A. Okay, I mentioned that a little bit earlier. But this factor of A is really made up of two different things. One of them is the orientation, and one of them is the collision frequency. Orientation was big um, in that last mechanism that we were looking at because the orientation was essentially flipping, right? Collision frequency, when you have two molecules, that is also then a big factor. So these two factors, depending on the type of mechanism, are big influences in this. So what we can do with the Arrhenius equation is we can gather data and we can plot it. Okay, and just as you know, any line or any plot will have a slope. That slope is going to be significant, and then the y-intercept is also a significant portion, and then you've got the x and the y values in there. So what are we plotting? Well, in this case, we're going to plot x as 1 over temperature, right? Uh, the natural log of k is going to be our y, right? So x was 1 over temperature. And then b is the natural log of a. And remember, these are components of the equation, right? A was a component of the equation. When you take the natural log of a, it drops out of the equation. You take natural log of k, the same thing. Sorry, let me start over again with that. When you take the natural log of the entire equation, right, you're taking the natural log of k, because k is just a number. You're taking the natural log of a. Again, a is just a number. But then EA over RT is actually dropping out of the exponential, right? Remember, our Arrhenius equation would have the e to the minus e sub a over RT. Okay, so we've rearranged that in terms of taking the natural log, and we come up with components for y equals mx. So if you have two different data points. One of the ways that you can one of the ways you can use the Arrhenius equation is, again, you only have to have two. In the previous slide, we had solved for when we have multiple data points and we want to graph that. But if you only have two data points, and so you have the rate constant at 2 and 1, and you have a temperature 1 and a temperature 2, you can rearrange this equation and you can essentially divide one by the other. And in doing that, once you then take the natural log of both sides, A is the same, right? And so ln of A over ln of A is 1, and so it drops out of the equation. So we don't have to deal with A. Okay. We already know that R is a constant. Okay. And again, the data provided will give you K1 and K2, and then the data will give you T1 and T2. So all we're left with in this case is E sub A, right? And so we'll be able to solve E sub A from this two-point form of the equation. Okay, so let's talk about collision theory in terms of kinetics. So for reactions to take place, there has to be the appropriate collision, right? And on average, in most reactions, you've got 109 collisions per second. But again, think about this. In that collision, what happens? When they collide, they may react or they may not. And that's going to depend on a couple of things. Whether the collision has enough energy to break bonds, right? Or whether the reacting molecules collide in the appropriate orientation, right, to form the new bonds. And so collision theory brings all this together. So you look at this, and you got all these molecules moving around, and they're all possible to react with one another. But the main reaction we're looking for is these three with those two forming something like this, right? That doesn't happen unless the orientation is correct, right? And the correct orientation is going to lead to, again, this activated complex and then potential coming off. So let's take a look at something like this NOCl reaction. So you've got NOCl, you got two NOCl's leading to two NOs and one Cl2. What's the mechanism here? So let's think about what a reaction mechanism actually is. A reaction mechanism is a description of what are the steps, what are the most important steps to this reaction going to completion. Okay. So if we look at a reaction like this one, where we've got H2 and 2 ICl, and that forms 2 HCl and 1 I2, and this should actually be a forward arrow here, right? And this is a forward arrow here, and this is a forward arrow here. The mechanism for this can be described this way. First, you've got H2 and ICl, and you form HCl and HI, okay? That would be one step. And then another step, you would have HI reacting with ICl to form another HCl and the I2. Okay, so this mechanism says that these are elementary steps And when you're starting to analyze these mechanisms, what you need to do is look at them in these broken down steps, right? And so these are what we would call elementary steps, and they can't be broken down into anything simpler. So the rate laws for elementary steps are important to be able to recognize. Each individual step is like its own little reaction with its own activation energy and own rate law. The rate law for an overall reaction you have to determine experimentally, but the rate law for an elementary step can be deduced from the equation of the step. So if we look at this reaction, right, this first one, where we have H2 and ICl going to HCl and HI, the rate is dependent on the H2 and the ICl, right? It's dependent on those two concentrations. But in the second step, right, the rate is only dependent on HI, okay? Because ICl is already there, okay? ICl is already there and HI has just formed, right? And so it's only going to depend on how much of that is formed. Okay? All right. Again, focusing on it's in these rate laws. So look at this table that describes rate laws for these elementary steps. So if you have an elementary step where you've got one reactant going to products, um, the rate law is rate equals K times concentration of A, right? If you've got two things, right? If you've got two A's going to products, that rate law is the rate is equal to K times concentration squared. And if you have two different, right, you have two different reactants in the elementary step, then the rate is equal to K times A times B concentration. So the overall, and the molecularity is basically saying the overall reaction rate. Okay. These bottom ones are pretty rare, and again, we won't talk a lot about those. I talked in our first lecture about how we'll pretty much deal with zero order, first order, and second order, right? And we'll continue that throughout these. So if we look at another reaction mechanism, and if we can break this thing down, and again, note that these have been, they didn't come through very well on the slide, and so they're the forward-headed arrows. So the overall reaction is in blue there. NO2 and CO go to form NO and CO2. The observed rate law is the rate is K times concentration of NO2 squared. Remember, this is from experimental data. But if we look at breaking this down into steps, right, then this first step looks like it should be the rate is K times NO2 squared, right? But this second one, okay, this second reaction, you get NO3, right, as a product of the first one. And this is also a fast reaction, right? And again, the CO is already part of, okay, the overall reaction. And so it is part of, it's already there, it's not involved, it's not created for this second step, right? So reactants that are created, let's say, for the second step are the only ones that we consider. Right? And so then this rate is equal to K2 times NO3. So if we again talk through this. Uh, what is the overall rate determining step, right? And that's what's going to contribute to this observed rate. Okay. So if we look at this and this is noted as being a slow step and this is the fast step, then the slow step is considered the rate determining step. It also then would have the highest activation energy. And if you look at the diagram, there's a high activation energy versus the second step that has the lower activation energy. And so this is going to govern how quickly we can get to products, right? Because again, this is the highest energy needed, the highest activation energy. The rate law, that first step, is what's going to be in the observed or the final or the mechanism, the overall step. Okay? Again, this is just blown up a little bit, but basically it's saying that the activation energy for step one is greater than that for step two, right? And so step one is going to have the smaller rate constant, and it's going to be the rate limiting. Okay. Okay. Oh, geez. This one's terrible. Let me see if I can get this to look any better. No. All right. So we're basically going to have to talk about this in lecture because of the way it came across. But essentially, what's being done on this slide, if you look at the actual PowerPoint on Canvas, what's being done on this slide is we're looking at how can the first step and the second step be combined. I'm sorry. How can the first step be um, rearranged so that you can find out from the second step how it correlates to the mechanism. Okay? And the reason you need to do that is because this N2O2, okay, that's created in the first step is part of the rate determining step. This says slow rate, right? When it says slow rate, that means that it is part of the rate determining step. It is the rate determining step. And so N2O2 is part of that, but it's created in the first step. And so you have to use the rate from the first step and you have to put it into the rate from the second step to get the overall rate observed. And again, we'll go through that in lecture. All right, let's talk about catalysts because we know that the rate changes with temperature, right? And we know that we can increase the temperature and increase the rate. What about other ways of increasing rate? And that's catalysts. And so, what does a catalyst do? Well, a catalyst reduces the activation energy. Okay, so reduction of the activation energy is the whole goal of a catalyst. And if you can reduce the activation energy in this case from this top transition state up here down to these multi-transition states at much lower energy, then that's going to be much faster, right? Because you have lowered the activation energy barrier. Right? Now, there are different kinds of catalysts. Some catalysts are homogeneous, meaning that they're put into the solution. Others are heterogeneous, meaning that they are a different phase than the solution itself or the reactants themselves. So if you look at something like the breakdown of these sugars, the breakdown of glucose and fructose from sucrose, right? How can we change that? Well, there's in a lot of the um, in a lot of processes within the body, there are things that we call enzymes, and these enzymes are built in such a way that their structure, their active site, is exactly matched to a substrate's shape. And so when these two come together, they're perfectly matched. This is a catalytic breakdown of this into these two different products. Okay, and so here's this sucrose in the active site. This starts to strain the bond between, right, the sucrose, I'm sorry, between the glucose and the fructose. And when that bond gets strained, it eventually gets broken. This is what is called a sucrase enzyme. Okay, so let's take a quick review. What we first were looking at is trying to talk about how to do a graphical determination of the rate law um, to find the activation energy, right? And so we can plot the concentration of a particular um, the concentration of a particular compound, right? And we can do that versus time, and we can do 1 over time. We can use that as part of the plot. Whichever plot gives us a straight line is going to help with the order, okay? And in helping with the order, we're then going to be able to figure that out from each of the plot fittings, okay? So if we get a straight line with concentration, plotting concentration straight versus time, then that would be the zeroth order. But if we go ahead and look at a first order plot, you would plot the natural log of the concentration of A versus time. And if you get a straight line with a negative slope, that's a first order. Okay, so something like this, where you've got the natural log of um, bromine over time. Okay. If you do 1 over bromine, if you plot 1 over bromine, you do not get a negative slope, right? So these integrated rate laws are going to be different for each reaction order. Okay. So we just started off by talking about what the integrated rate laws might look like, but the integrated rate law for zeroth order, right, is this. For first order is this. For second order is this. Okay. We can also determine the units of K for each order, and then we can also talk about what we call the half-life expression. Okay. All right. So one of the things that we could ask is, what is each of these? Uh, what are the labels in each of these, right? And over here, you should be able to label this. You should be able to label this, and you should be able to label this. And then this is essentially the energy of the reaction, right? net interaction. Again, we know that temperature is with the rate constant. We know that the reaction progress, right, is there's the energetics involved with an activation energy here, an activation energy here, and then the difference in energy between reactant and product. Those are the things that we can look at. Reaction progress meaning essentially over time. All right.